Hello once again, this is Teacher Juma. We proceed to lesson number 5. So in lesson number 5, we are going to look at definition of some terms or some enthalpies. So the enthalpies that we are going to define are the following: molar heat of solution, molar heat of combustion, molar heat of displacement, molar heat of neutralization, enthalpy of formation, atomization energy, lattice energy, and hydration energy. So let me just bring these ones closer to the screen so that as we discuss, you also read along. So let's start with heat of solution. So by definition, the molar heat of solution is the enthalpy change that occurs when 1 mole of a substance dissolves in a solvent to give an infinitely dilute solution. Then molar heat of combustion is the next one. It is the enthalpy change that occurs when 1 mole of a substance is completely burned in oxygen. Molar heat of displacement. This is the enthalpy change that occurs when 1 mole of a substance is displaced from a solution of its ions. Then we have molar heat of neutralization. This is the enthalpy change that occurs when 1 mole of ions of hydrogen ion is completely neutralized by an alkali. So take note, there is in each case there is the use of molar heat of. So when the term molar is used, 1 mole of a substance is involved. So without the addition of molar, let's say if it was just heat of solution, then you just say that it is the enthalpy change that occurs when a substance dissolves in a solvent to give an infinitely dilute solution. So without having to mention when 1 mole of. Same for heat, molar heat of combustion. So if it is heat of combustion, you will just say it is the enthalpy change that occurs when a substance burns completely in oxygen without necessarily mentioning the word 1 mole of. But when the word molar is there, you have to state that when 1 mole of a substance is involved in that case, except for heat of formation, as we discussed in the previous lessons. Formation, always you have to mention 1 mole of that substance being formed from its constituent elements in their standard states, even if the word molar heat of is not there. Even if the word molar is not there for formation, you always have to state molar of. But for this other type of enthalpies, if molar is there, then in your definition you must incorporate the word 1 mole of. But if the word molar is not there, then you omit that part, 1 mole of. Okay, enthalpy of formation. For formation, this is the energy change that occurs when 1 mole of a compound is formed from its constituent elements in their standard states. Now, as I've mentioned, see here for enthalpy of formation, unlike the other enthalpies, there was molar enthalpy of or molar heat of. But for formation, you see the word is just formation. There is no molar attached. But in your definition, you have to incorporate that word 1 mole of. Atomization energy. This is the energy change that occurs when gaseous atoms are formed from their elements in solid, liquid, or gaseous state. Lattice energy. Lattice energy. This is the enthalpy change that occurs when 1 mole of an ionic compound is formed from gaseous ions. And note that this process always releases energy, or it is exothermic. I'm going to explain this in the lesson that we shall be dealing with the Hess law. We'll elaborate on that, why it is exothermic. Then hydration energy. Hydration energy. is the energy change that occurs when gaseous ions in ions become completely surrounded by 1 mole of, when surrounded by molecules of a solvent. So I'll repeat that. Hydration energy is the enthalpy change that occurs when gaseous ions become completely surrounded by molecules of a solvent. So these two, lattice energy and ionization energy, I'm going to elaborate on them under Hess law. Okay, so let's move to the next part, that is quantitative determination of enthalpy. Now, this section is very crucial in energy changes. There are so many questions that are tested from this area, and it involves calculation. So quantitative, so this we are going to have quite some calculations to do. So quantitative determination of enthalpies, how we determine enthalpies empirically or through experiments. First is there is a formula here that we use for calculation of enthalpies. So the enthalpy change is determined by this expression. So you take the mass of the solution, multiply by specific heat capacity, we give it letter C, you multiply by the change in temperature during the experiment, so that is denoted by delta T. So the sign delta, as I have explained in second lesson, I believe, it refers to change in. So change in, T is for temperature. So in symbols, so change in enthalpy, H we say this for enthalpy, this sign is for change for enthalpy, H. So change in enthalpy will be determined by, you take the mass of the solution, multiply by specific heat capacity, then multiply by change in temperature. So the formula of the expression becomes delta H equals mc delta T, or you can also express it as delta H equals to mc theta, where theta is the change in temperature. So during the experiment, there are some precautions that you have to take. One of them is this one. When the beaker that we are using to carry out the experiment for heat change, to determine the change in heat, you do it, you wrap that beaker with a tissue paper. That process, we call it lagging. So when you lag, that minimizes the heat loss. And if it is the enthalpy of combustion, then you do what we call drought shielding. Around the flame, you can use carton boxes. You put them around the flame to prevent the heat from being blown away by the wind. That effect is what we call drought shielding. Let me just illustrate this one, lagging, how to do lagging. So this is a plastic beaker. Let's say this is where we're going to use for the experiment. So the solution will be inside there. Then you take tissue paper, So what you do is you just wrap around that beaker. You wrap it like that with the tissue paper. And then you can fasten this using a rubber band like that to hold it in position. So the essence of doing this is to minimize heat loss, because your body can absorb some heat energy that is being generated from the reaction or by the reaction, or the other way around, also to prevent you supplying too much heat, so that a lot of heat is supplied by your body. We preferably use plastic, because plastic is a poor conductor of heat, much poorer than glass. So that's why plastic beakers are preferred. So this process, or doing this is what we call lagging, and it minimizes, because a tissue paper is also a poor conductor of heat. This minimizes loss of heat to the environment. So the next part, let's look at now examples involving this formula, see how we are going to calculate using that formula. we look at those examples. So the first example will be on enthalpy of solution. So here we are going to look at two examples under enthalpy of solution. So the first one is this one. When 2 grams of ammonium nitrate is dissolved in 100 ml distilled water, the temperature drops. So you mark this, the temperature drops. When the temperature drops, it means the reaction is endothermic. You will see how to deal with that. So it drops by 1.5 Kelvin degrees Celsius. So given that the specific heat capacity of water is 4.2 kilojoules per kilogram per Kelvin, calculate heat of solution. So to calculate the heat of solution, so we use the expression that we have just mentioned a while ago. Delta H is determined by MC delta T. So where we say M is the mass of the solution. So when it comes to the solution in this case, so M is the mass of water. So here, to take note also, though not given, usually density of water is 1 gram per centimeter cubic. 1 gram per centimeter cubic. Because what you have been given here is in ml, so this is equivalent to centimeter cubic. 1 ml is equivalent to 1 centimeter cubic. So this is like 100 centimeter cubic. So first we need, so M will be the mass of water, so we need to determine the mass of water. And here we will determine the mass by using this expression. Mass is equivalent to density times volume. So the density of water is 1 gram per centimeter cubic. So the mass is going to be 1 gram per centimeter cubic. 1 gram per centimeter cubic times the volume of water is 100 centimeter cubic or 100 ml. So per centimeter cubic cancels with centimeter cubic. So therefore the mass is going to be 1 gram times 100. That gives us 100 grams. Now look at the specific heat capacity given. It is given in kilograms. So therefore you will need to convert this one into kilogram. So to convert this into kilogram, you divide by 1,000. So you divide this by 1,000, it changes the grams to kilogram. So this would be equivalent to 100 divided by 1,000. So that will be 0.1 kilogram. So therefore, now we can calculate the mass, the specific heat capacity. So the H will be the mass of water, 0.1 kilogram, multiplied by specific heat capacity we have been given here, 4.2 kilojoules per kilogram per Kelvin, multiplied by the change in temperature is 1.5 Kelvin. So in this case, you can cancel the units. Per kilogram with kilogram, per Kelvin with Kelvin. So that leaves us, this will be the unit for our answer. So we take 0.1 multiplied by 4.2 multiplied by, so if you multiply that 0.1 times 4.2 times 1.5, so the answer will be kilojoules. So we multiply that. So 0.1 times 4.2 multiplied by 1.5. So that gives us 0.6 3 kilojoules. Then at B, we have to calculate the molar heat of solution. So to calculate the molar heat of solution, you determine the number of moles present in the mass given. So the mass given here was 2 grams. So to get the number of moles, we can calculate the number of moles using the expression mass over RFM. So the formula of ammonium nitrate is N4 NO3. So to get the RFM, so you add the masses for each individual atoms there. So we have nitrogen 14 plus hydrogen 1 times 4 4 plus nitrogen 14 plus oxygen 16 times 3, that gives you 48. So if we add in this case, so that comes to 80, that is the RFM. So therefore, number of moles will be the 2 grams divided by 80. So 2 divided by 80, that gives us 0.025 moles. Then now from there, we can determine the amount that 1 mole will liberate. So in this case, we will say if 0.025 moles liberates, in fact not liberates, this one absorbs, as we have seen. From here the temperature dropped, so heat was absorbed, so this one absorbs this amount of heat, 0.63 kilojoules. Now 1 mole will absorb let's say X, then we cross multiply. So by cross multiplying, so we are going to have therefore, so we take this like that, so you have 0.025x is equivalent to 1 times 0.63. So divide by 0.025 divided by 0.025. So if you divide, so that will be 0.63 divided by 0.025. That will give us 25.2 kilojoules. Now, this one now we will say per mole, kilojoules per mole, because it is now for 1 mole. But here, this value here we did not say per mole, because it was not for 1 mole. This was the value for the 2 grams of ammonia that was dissolved. But if we dissolve 1 mole, which will be equivalent to 80 grams, then that will give us this amount. So this then is what we refer to molar heat. And for molar heat, you have to indicate the sign. So we have seen that here the temperature dropped. So if the temperature dropped, it means the reaction was endothermic. So we say endothermic reaction, we assign a positive sign. So this plus sign indicates that the reaction was endothermic, meaning it was absorbed. That is why the temperature dropped. Okay. So we will consider the next example. So we will go, so this will be the end of lesson 5, then now lesson 6. We look at another example of gate solution.